Okay, so I have the distinct pleasure to welcome Professor Gabrielle Russo to SoMAS for today's seminar. As you can see, Gabrielle is an associate professor in the Department of Anthropology here at Stony Brook. She is also deputy director of the Turkana Basin Institute, which you're going to hear a lot about. Gabrielle did her PhD at UT Austin some number of years ago, 2013, seems like just yesterday.
It doesn't.
Professor Russo is an expert in the functional anatomy of primates and their skeletal evolution, focusing on hominoid evolution. Her recent work has focused on the Miocene, that is from about 5 to 23 million years ago. And much of her work is being conducted at Napudet, in northern Kenya, a site rich in fossils from the Miocene epoch. So the title of her talk you can see, but I can read it to you. Planet of the Miocene Apes, the Paleoanthropological Significance of Napudet, Turkana Basin, Kenya. So I just want to say also that I personally begged Gabrielle to come speak with us because we're always thirsty for hearing about really cool science. But there are some of us here who are interested in research opportunities, and SoMAS has some ongoing research activities at TBI. And there are also lots of educational opportunities, including for undergraduate students. So Gabrielle will also tell us about how amazing TBI is. It truly is. She'll also answer important questions like, I don't know, what is a sea wolf and what is an anthropologist and other things. So please welcome Gabrielle to SoMAS.
Thank you. And this. Should that do it? Hello? 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 Is there back there? Is there back there? No, not worried. Sure. I think it's on. Fine. I can also just talk really loudly. The light is not on. Yeah, the light is on.
I know, but you can't hear it on Zoom if you don't.
Oh,
Plug
yeah.
in my call.
This is. It's on all. Oh, yeah, there we go. Maybe I was too far away. Should I move this?
Yeah.
There you go.
Yeah.
Can everyone hear me now?
I think that's good.
Okay, so the speaker, the microphone is working.
Yes.
Okay, thank you very much. All right, thank you. Yeah, I'm great. All right, good morning. Thank you, Dean Shepson, and thank you all for being here. As mentioned, I am an associate professor in the Department of Anthropology. I've been here since 2014. I am core faculty, one of 4 in the SHAPE lab in the department, which stands for Studies in Human and Primate Evolution. My research focuses on ape and human functional anatomy and evolutionary morphology. And as mentioned, I also am deputy director for Turkana Basin Institute, and I've been in that role since last year, and previously before that was working as associate director. Okay, so the main question that many folks might have in this room right now is why a biological anthropologist has been invited to speak at the SoMAS Colloquium. And perhaps in particular, a biological anthropologist whose main area of study is ape and human evolutionary and functional morphology. So I'd like to take this first few slides to sort of walk you through what my overarching goal and theme of today's talk will be. Well, fully understanding the evolutionary and functional anatomy of our ape ancestors obviously requires the fossils themselves, but it also requires a deep knowledge about the past environments in which they moved around, ate, found their mates, evaded predators, and so on. Part of my research since 2017, so actually a few years after I arrived at Stony Brook, has included fieldwork at a site in the Turkana Basin called Napudet, which as mentioned is in northern Kenya, and it dates to the Middle Miocene at about 13 million years. And I'm drawn there because Napudet is notable for preserving fossils, including ape fossils that are of considerable importance to this particular time period in ape evolution. And I'll explain a little bit more about why that is in a bit. Now, Napudet is just one of many fossil sites of paleontological significance in the Turkana Basin, which is a hydrographic and sedimentary system located in northern Kenya. It's one of the hottest places on the planet, with a mean annual temperature of nearly 30 degrees Celsius, so 86 degrees Fahrenheit. And at the center of the basin is Lake Turkana, the world's largest permanent desert lake that receives most of its waters from the northern Omo River, and it has no outlet, so i.e. it's a closed basin. You can see here that Napudet is located on the western side of the lake, just below one of the field sites, or just south of one of the field sites, and south of the Turkwell River. Given the extreme climate of the region, the presence of the world's largest permanent desert lake, the Turkana Basin is a rich area for study for not just the paleo, but also myriad other sciences. And my work, along with the work of many others, is made possible by the infrastructure and support of one of Stony Brook's most unique research institutes, the Turkana Basin Institute, which has 2 field stations, one of which is on the west side, and that's shown here, TBI Turkwell, and one on the east side. And so what I'll do today is weave together a bit of information about my own research program on ape evolutionary and functional anatomy, how I got involved in TBI years after I actually came to Stony Brook after my hiring here, and how folks from multiple disciplines and varying degrees of field experience can capitalize on TBI's infrastructure to help carry out their own research projects. Very briefly, for those of you who are unfamiliar with what TBI is, it's a research institute founded in 2005 by Richard Leakey and Stony Brook. Shown up at the top right is Richard Leakey receiving his honorary doctorate in 1998 with then university president Shirley Kenny. On the bottom, Richard Stone with Shirley and his wife, Neve. And in terms of what TBI does, it enables, supports, facilitates year-round research, field research, and education by providing permanent infrastructure for interdisciplinary study in what's one of the world's most significant natural laboratories, the Turkana Basin. Since its founding, TBI has served as a beacon for international scientific research in remote northern Kenya. And you might recognize the name. It is best known for its long-standing research in ape and human evolution, with many of its research projects focused on paleoanthropology and the study of the fossils themselves, its geological context of those fossils, and archaeology, the investigation of those material remains perhaps found with those fossils. The paleosciences continue to be a strong primary focus of the Institute. Among some of the ongoing projects still happening in the basin include the long-running Kubi-4 research project headed by the Leakeys and now with PI Louise Leakey and Jennifer Kamoya. Hominin footprints in the Turkana Basin. You may have heard or read about this publication in last year's news, suggesting different human relatives living alongside one another. The West Turkana Miocene project, which investigates ape anatomy and evolution. Work on the geochronology of the Turkana Basin, including marine fruens conformity project. Others include the hominin occupation in their economy region, and then archaeological projects, including ones that look at the later prehistory of West Turkana. And the West Turkana Archaeological Project run by PI Sonia Harmond. And this is the site where we find to date the world's oldest stone tools, dating to roughly 3.3 million years, known as the Lamechwian tool. However, since TBI's inception, it's also broadened its research scope to include studies of modern day climate and people. This includes the work on Lake Turkana by the Lake Turkana Research Project, headed by SoMAS faculty and students, as well as the work by the Turkana Human Health and Genome Project. And the latter actually just published a study paper that made the cover last week, I think now, of Science, with research that uncovers the genetic signatures underlying adaptations to arid living, where heat and water scarcity pose constant challenges to these pastoralist communities and the adaptations to surviving in those conditions. So that's an overview of what TBI is, its sort of general focus. And now I want to switch back to a bit about my research program, which started with a focus on predominantly museum and lab work, including experimental studies. The ultimate goal of my research program is to address questions that inform our understanding of what are major adaptive shifts in the locomotor skeleton during the course of ape and human evolution. And much of my work focuses on the axial skeleton, and that includes the head and the vertebral column for a number of reasons. One, it's the core of the locomotor skeleton to which the arms and the legs all connect, as well as its morphology and function is diverse among primates, including the two primates you can see here, and these differences in postures and locomotor behaviors reflected in their axial skeletal anatomy. But perhaps most importantly, the morphology of the axial skeleton shifts fundamentally throughout the course of primate and human evolution. And often these shifts are associated with the appearance of new adaptations and new primate clades or primate groups. So your work on the axial skeleton thus has sort of both functional and phylogenetic implications for understanding ape and human evolution. I want to discuss the three specific sort of evolutionary shifts or transformations that I'm interested in that bear directly on ape and human evolution. But to sort of situate you or orient you first to how I'll talk about it, I'll describe what this simple diagram is showing primate relationships. So all the way out on your left, a group, our most distant primate relatives, the prosimians, including our lemurs, lorises, and galagos. Then our South and Central American monkeys, African and Asian monkeys. I have extinct basal apes, our crown apes, so those that are most closely related to our living apes and including the living apes themselves. And then of course hominins, which includes modern humans and our extinct bipedal relatives. So one of the most dramatic shifts that we see in the axial skeleton during human evolution is obviously the adaptations to bipedal locomotion or walking on two legs. All hominins, by definition, are characterized by bipedalism. And so our ability to detect this form of locomotion in the fossil record bears directly on knowing who our earliest ancestors were. And so much of my research has focused on identifying these adaptations to upright posture, both looking at the base of the cranium, where the skull connects directly to your upright trunk, as well as the lower back, in which you see features like lumbar lordosis, curvature in the lower back, the adaptations required to balance your torso over those two legs. I'm also interested in the adoption of more upright trunk postures, which characterizes crowned apes and distinguishes them from all earlier apes. These upright trunk postures we call orthograde positional behaviors, in which the trunk again is held much more upright than monkeys or earlier apes, in which that trunk is held horizontally. The ability to identify orthograde positional behaviors or these upright trunk postures bears directly on our ability to identify apes of a modern aspect or those apes most closely related to crowned apes. And so again, much of my research has focused on identifying those adaptations. How do we sort of disentangle what are adaptations to bipedalism versus adaptations to orthogrady itself? And I've done quite a lot of work on this, including using comparative approaches, looking at other animals like giant pandas that also use upright postures to look for instances of morphological convergence. Finally, all apes, and you don't need to be a scientist, most of us have recognized this one, all apes living and extinct are noticeably characterized by the absence of tail. Tails are present in most other mammals, including most monkeys and lemurs. What's important is that tail loss is actually one of the very first ape-like features that appears in the fossil record, before you get a lot of those other ape-like postcranial characteristics. And so in a lot of ways, these earliest apes actually look much like monkeys, but without tails. And so the ability to identify who the earliest hominoids or earliest apes are includes the ability to attribute things like tail loss or tail length reduction to extinct taxa. And so in order to contextualize tail loss and understand tail length variation, much of my work has also focused on identifying correlates of tail length variation, including tail presence, tail absence, as well as the ecological and behavioral factors that actually underlie the evolution of tail length reduction. So these questions drive a lot of my research program. I'm interested in broad questions that also relate to these specifically with relation to the axial skeleton. But to do so, I employ again a number of frameworks, including comparative approaches like the one I described, investigating sort of orthograde positional behaviors in other mammals and how they may morphologically converge or not with things like our orthograde apes. Experimental studies to test for those actual mechanical links between form and function relationships, ontogenetic studies, and as well as evolutionary work in which I've applied a lot of my work that I've done on living primates and the relationship between form and function on living primates and other animals to interpretations of the fossil record. This continued up until through my hiring at Stony Brook. I was hired in 2014. Much of my earliest work was done in collaboration with folks over in anatomical sciences, with a focus on what was then known as the Primate Locomotion Lab. However, the anthropology department's proximity to Turkana Basin Institute, which is located on the same floor, both on the 5th floor of SBS, meant I had nearly weekly visits by both Richard and Lawrence himself, semi-regular dinners, always asking, when are you going to come to the Turkana Basin and do field work? For the first couple of years, I happily evaded these questions and continued to do my work in the air-conditioned museums and labs that I was very much enjoyed. But around 2017, Stony Brook hired a research professor, Isaiah Nengo, who tragically passed away a couple of years ago, who had just made a splash in the ape evolution world with the publication of a Miocene ape infant cranium. It is still to date the most complete ape cranium from the Miocene. And because it's an infant, it has bearing on our understanding of the ontogeny of the cranium. This cranium brings us back to Napudet, which is the location from where this cranium derives. And a year after the infant ape cranium was discovered, Isaiah and his team started to recover a postcranial skeleton of an ape from a site now known as NP109, or a locality known as NP109. This is a photo. I use this in my title slide. These are the Napudet Hills for which this site is named. And shown all the way on the right is the site or locality NP109. And in the red box, you can see what of course piqued my interest. That's a lumbar vertebra coming out of the ground, which was excavated in 2015. Okay, so why was I so interested all of a sudden in this discovery by one of my new colleagues? Well, the Middle Miocene, and in particular the date that Napudet is dated to at 13 million years, is a particularly important period in hominoid or ape evolution. It's the time when we see a movement away from the more horizontal trunk postures of earlier ape taxa like proconsul, akembo, Afropithecus, toward the behaviors of what we see in crown apes and late Miocene hominoids, which include the more orthograde positional behaviors, things that you see in pan, gorilla, etc. And among the fossil apes, most of those fossils that exhibit these adaptations to orthograde positional behaviors have to date been found mostly in Europe, which has also had a bearing on our biogeographical hypotheses about African ape evolution. So this time period in the Middle Miocene is when we should expect to see postcrania skeletons of apes that should tell us or show us about what these pathways looked like on the way from these more monkey-like quadrupedal behaviors and postures to becoming more like modern apes. In Africa and Eastern Africa, there are very few sites that actually date to the Middle Miocene, and in particular, in the Turkana Basin, it includes really scant remains of just a few taxa, including Equatorius, Chenopithecus, and Cholopithecus. These taxa for Chenopithecus, there's really just a distal arm bone. There are partial skeletons for Cholopithecus and Equatorius, but they're considerably crushed and distorted, which have made comparisons of those skeletons quite complicated from a quantitative perspective. So these aside, there are actually no other reported ape postcranial remains from East Africa that date between 15 and 7 million years. And again, part due to this paucity of Middle Miocene localities. So this really underscores why I'm particularly interested in this postcranial skeleton that dates to 13 million years and is found in the Turkana Basin, and the PI of which that project then now happened to be in my department. So this is essentially how I got lured in to doing field work. I joined the Napudet research project in 2017. Here's a photo from one of the first few field seasons I did, excavating at the locality where this ape postcranial skeleton was found. Up until this point, I had zero fieldwork experience in Africa. The only fieldwork I had done before was a brief excursion in the Bighorn Basin working at an Eocene primate site. But I'd never really been out, never done fieldwork out in Africa for sure. It didn't take me long to realize a couple of things. One, linen is a really terrible fabric to try to wear out in the desert and do fieldwork in. And two, sandals are an equally terrible clothing choice for trying to hike around the desert due to both the dirt and the sun. Because of TBI's infrastructure and the clothing advice of many of my collaborators, now colleagues and friends, I was eventually able to comfortably continue doing that research since 2017, and it continues to be a pretty important part of my research program to date. We ended our excavations of the primate postcranial skeleton in 2022. So really this work in recovering this primate skeleton took up a large part of the next few years of my research. What's shown here on the right are some of the more functionally informative parts of the skeleton, and includes parts of the vertebral column, the ribs, the shoulder joints, the elbow joint, hip joint, ankle joint, elements of the hands and feet. In total, we have more than 70 postcranial specimens. There are no craniodental remains, so right now our ape remains nameless. I'm a little too conservative to just attribute a name, a taxonomic name to it. So it remains nameless, but we do have a large part of the postcranial skeleton, which means there's much we can tell about how this ape, from this very significant period in ape evolution, moved around. So I'm pleased that last year we finally got this published in the Journal of Human Evolution. And what did we find? Well, based on a functional morphological analysis of its skeleton, from the femoral head, which is shown all the way here on the right, I can tell that this ape had a particularly mobile hip joint, meaning that in an arboreal environment, it could move its hips around in many ways and motions that a monkey or your cat and dog certainly can't. The lower back was adapted for more upright postures, and more upright postures than you see in monkeys or earlier Miocene apes, like proconsul, like Akembo. The ape has large mobile elbow joints, meaning it can supinate and pronate its forearms, which is going to be useful for clambering around trees, clambering around arboreal environments. There's well-developed grasping of the hands and feet, again, also useful for climbing. And what we call an inverted foot posture, meaning that the feet at the ankle joint could turn inward, another really useful feature for climbing up vertical trunks or climbing throughout the trees. So I was very excited to lead this project and expand my expertise in ways beyond the axial skeleton to other regions of the body as well. Okay, so to this point now I've described a little bit about my research, how TBI was really able to support me during my first foray into fieldwork, such that it is now successfully integrated as a major, if not the major part of my research program. So now I'd like to share a bit with you about TBI and really what made that possible. As I've mentioned, TBI has 2 field stations in the Turkana Basin, but its support system actually starts here at Stony Brook. Stony Brook serves as its international administrative and academic headquarters. To date, we have 5 tenured or tenure-track faculty, including 2 in anthropology, 2 in geosciences, and 1 in E&E. We have another incoming faculty member in E&E, a drylands ecologist who will be joining us in spring of 26. But of course, as you know, including members from your own academic unit, we have faculty and students affiliates across the university and a number of other places. Abroad in Kenya, TBI's administrative offices are located in Nairobi. And the Nairobi office is important for really getting us past that initial hurdle, the thing that really makes fieldwork complicated for those who know nothing about doing work in another country. They assist with things like permissions, research permits, governmental relations, helping with logistics, procurement, reservations, flight operations, which I'll talk about in a moment, as well as budget management. And I'm also pleased to share with you that the TBI Nairobi office is also starting to support what are hopefully just the beginning of a suite of analytical facilities that will be available, including what's shown there on the left, which will be East Africa's first stable isotope lab. This is with collaboration with Kevin Uno from Harvard University. We also have the development of a micro CT lab also underway. But of course, the real gems of TBI are the 2 research stations, the field stations themselves, that include TBI Turkwell on the west side, shown on the bottom left. This overlooks the Turkwell River. It's a short drive from some sites called like Lothagam, the site that I work at called Napudet. And it can be accessed by commercial flights that actually go from Nairobi into a nearby town called Lodwar. The TBI Illirat Field Station is on the northeastern side of the lake. It's certainly more remote, but this field station, again, this can be accessed by Air Turkana, which I'll show you a photo of in a minute. And you can also use Air Turkana to fly between the field stations if you need to. So to provide transportation both between field stations, facilities across the lake, TBI has a Grand Caravan that provides charter service for its TBI affiliates and its researchers. So a bit about the field stations themselves. They're actually pretty deluxe accommodations as far as I'm concerned, with food service, laundry, security, internet, stable internet, electricity, and so on. In order to keep the fossils themselves in the places that they're discovered and recovered, TBI also houses fossil collections at each of its field stations. They're managed by our expert managers, including collection supervisor Martin Carinia. Here shown on the bottom left are some of the collections housed at TBI Illeret, and on the right are actually part of the Napudet collections that are housed at TBI Turkwell. In addition to housing the things you might be working on, it also includes technical services like fossil preparation. So here a fossil is being prepared out of a plaster jacket that was taken back from the field. On the right, a 3D scanner, a 3D Artec space spider scanner is making a 3D model of the elephant cranium that's shown there on the right. And then, of course, there are things like classrooms, labs, various buildings where you can actually carry out and conduct your work. The photo up on the top right is from a part of the lab spaces we call the vault, which is where we keep the actual primates that are recovered from the sites out at TBI Turkwell. And if you're going into the field and spending a number of weeks out of the field stations and camping elsewhere at the sites you're working, TBI also is responsible and offers camping equipment, all from things from tents to the actual kitchen setups themselves, to any of the materials, equipment, or supplies you might need to actually do the work out in the field. And it can get you those places with a number of its vehicles. The lorry shown here on the left, this you can see what they're taking out right now. We're at Napudet. They're moving barrels of water that are brought out to our field site where we'll have clean water for drinking and so forth while we're in the field. On the right is a sort of far away photo of a Land Cruiser. It turns out the only time I take pictures of our Land Cruisers are when they're stuck somewhere or broken down. So I've found one photo in which our truck seems to be operating just fine and we aren't trying to push out of a sand dune. So that's the one we're going with. One of the most impressive things about being at the field stations are the two hydroponic gardens. There's one out at Illeret and one out at Turkwell, which provides us with fresh fruits and fresh vegetables. It's kind of amazing to be out in the middle of the desert and be served watermelon for dessert. So it's very impressive. Shown up on the top right is cold room storage. It's solar powered out at Illeret for storing things, the fruits and vegetables, to keep them fresh. And then shown on the bottom right is some of the solar panels out at Turkwell. Turkwell is now almost 100% entirely powered by solar power. So again, just to show you an overview of both of these field stations. Turkwell, right next to the meandering Turkwell River, it can accommodate up to 100 people at a time, including our support staff. And then TBI Illeret is located a few miles from Illeret Village, which is close to the Kenya-Ethiopia border. At full capacity, it's slightly smaller, about 70 individuals, including support staff. And I love this photo on the right because it really shows you just how close TBI Illeret is to Lake Turkana. So here's a photo of one of the researcher cabins, and you can see the horizon of Lake Turkana in the background. And of course, none of what we do or can enjoy out at the field stations is possible without the incredible work of our staff, ranging from the mason to the driver to the gardener to the house cleaner, to our dog out at Turkwell, Tupac, who provides us with emotional and moral support during our field seasons. I also want to mention the close engagement that TBI has with its communities. There are community liaisons with both field stations that work closely with the host communities that graciously allow us to do our work there. TBI also works closely with the governments, the local governments in Turkana and Marsabit counties, in order to make positive and sustainable changes in the lives of the people that surround Lake Turkana, and again, graciously host us there to do their work, our work. We provide support in a number of ways. Over the past few years, we've provided scholarships to hundreds of high school and university students, as well as support to some of the teaching staff. On the bottom right, you can see TBI's mobile clinic. This is out of Illiret. Illiret also has a solar reverse osmosis system. We provide logistical support for borehole drilling just outside of TBI Turkwell. And all of these things help to create greater access to health services, drinking water for those communities. And again, these are just some of the initiatives to show you the ways that TBI is engaged. To turn just a bit to the experiential learning opportunities that can be carried out of Turkana Basin. Our sort of standard or the GEM original program of TBI is our Human Origins program. It offers both anthropology and geology courses, and focuses on archaeology, paleontology, geology. It's sort of our human evolution field school. We're also proud to host the Global Innovation Field School. This is run by faculty out of the engineering department. This is a field school in which students study multiple engineering disciplines that relate to infrastructure development, helping to assess natural resources, evaluate potential to support human development, economic independence. And there are some of the key technical areas of things that students cover include construction technologies, transportation, contamination, hygiene, the quality and quantity of water, and so on. The semi-arid climate of northern Kenya means we have some amazing sky views at night, which puts us in a very competitive position for astronomy observation and research. In collaboration with DARA, the logo here on the bottom right, Development in Africa with Radio Astronomy. We're proud to have run, in the first couple of years, our astronomy field schools. They run out of Illiret, which is what's shown there on the right. And this is not a doctored photo, that is the sky out at Illiret. No filter needed. And this past January, we were pleased to offer for the first time to host the Stony Brook Simon STEM Scholars. This is an honors program at Stony Brook with students from many different academic backgrounds, including students from psychology, biochemistry. We had a marine sciences student out previously. It was my pleasure to be a part of this in its inaugural running out at TBI Turkwell. I'm excited that the students are shown here actually at Napudet. So shown on the right are the students standing with the columnar basalt that provides us with the argon-argon date of that 13 million years. And then shown here on the left are students standing with what is one of the most sort of impressive and exciting things about Napudet, which is its fossil forest. So this is a fossil tree stand, a tree that is actually still in situ in the ground. And there are many of these across the landscape at Napudet. So this brings me back around to Napudet, and I'm excited to share that my work there continues. It's expanded quite a bit since my start, and now wouldn't be possible without the work of collaborative efforts of a very wide network of individuals. And this slide is really only able to capture some of those. And so I want to spend the last few minutes just sharing with you a bit now about where I've gone with my research since getting to Napudet and since the publication of this postcranial paper, and how it has sort of become an integrated component of my research program. This photo is from about almost exactly a month ago. Napudet Research Project joined forces with the Lothagam Research Project we are funded now by a TBIRF Simons Foundation grant to carry out some work that's looking at the relationship between these two sites. I'd like to point out that I am now very properly dressed for the fieldwork for the occasion of being out in the desert. So these two sites, Napudet and Lothagam, are geographically quite close to one another, and they're hypothesized to potentially share some of the same source volcanics, such that part of the work we're working on together as a collaborative team is investigating that correlation, both from sort of geological, looking at biomarkers, looking at the vertebrate paleontology, and so forth. I mentioned the Napudet fossil forest. Here are some photos shown on the right of, again, the fossil trees in situ, the stands that you can see out in the forest. Here's a beautiful leaf photo taken by Greg. Actually, a lot of these photos have been taken by Greg, showing you a nearly perfect imprint of a fossil leaf out of the Napudet sediments. Why are we so interested in this? Why am I so interested in this fossil forest? Well, this fossil forest is found in the same sedimentary horizon as some of the ape fossils that we're interested in, which means that, to go back to sort of the beginning of my talk, this is the opportunity to link together not just the anatomy of the fossils and what we can tell about how they moved, but the direct environments in which they did that. So to be able to reconstruct what kinds of trees they were, how close were these trees together, what was the actual environment in which the apes that we have found can move around, can find food, can find mates, and so on. I also have an ongoing project on the Middle Miocene climatic optimum. This is a warming period that's touted as potentially the best analog for current climate change. I'm working at, and this occurs about between 17 and 14.7 million years. Based on the paleontological record, we also know this corresponds to what is a large faunal turnover on quote unquote events. I am collaborating with Ellen Miller out at Wake Forest University. She's PI at a site called Bullock, which is also in the Turkana Basin. It dates to 16.7. So Bullock documents a fauna that are essentially on the cusp of the Middle Miocene climatic optimum. And then Napudet at 13 million years documents a fauna that are essentially in the aftermath of this Middle Miocene climatic optimum. So together with published faunal data from other sites, including Kapsaramon and Mboko, we're essentially looking together and capturing faunal change at 500,000 year increments to provide sort of what is an unprecedented resolution to the African fossil record. We're integrating taxonomic and ecological data, and we'll be testing things about lineage-specific changes, including, for example, this time period also capturing when we moved from those more horizontal trunk postures and behaviors to the more upright postures we see in modern-day apes. Finally, I want to point out that all three of the sites that I've mentioned, Napudet, Lothagam, Bullock, are all part of a much larger project called the Turkana Miocene Project, and that is run by former PI Isaiah Nengo, Greg Hengus here at Stony Brook, and external collaborators Kat Beck, Chris Colson, Craig Feibel, and Kevin Uno. The goal of the TMP, it's looking across many Miocene sites in the Turkana Basin. in efforts to evaluate the effects of climate and tectonics on the evolution of mammals, including apes and early hominids. And this is using an integrated approach that involves specialists in the areas of, I love these sort of team names, Earth, climate, and life. And my role in this particular project has been in the life team with offering my expertise now in primate paleontology. One of the things that I love about the TMP is the really wide range of collaborators, not just paleontologists, but scientists across so many disciplines and so many institutions. I want to end by talking about the TMP because I think it really exemplifies the kinds of large scale, large impact types of projects that can be carried out with the support of Turkana Basin Institute. So let me return to the question of what does TBI do? Well, with the modern day Turkana Basin, including Lake Turkana, I want to underscore again its potential as an area of study for not just the paleosciences, but many other sciences. There's incredible opportunity to continue expanding work in areas of climate and climate solutions, environment and sustainability, ecology and evolution, human health at extreme energy loads. We have an incoming faculty member in anthropology who studies pregnancy and women's metabolism in populations of individuals that live on the east side of the lake, and how women maintain or deal with that energy load at these extreme temperatures. So lots of interesting questions that can be investigated in the Turkana Basin. And just to underscore the importance of thinking about these questions, this kind of research in Kenya, I'll sort of end here with this quote from a recent New York Times newsletter that asked 6 world leaders who are confronting climate change, what it means for them. And in this interview was Kenyan President William Ruto, who notes droughts made millions of Kenyans go hungry. Floods just killed the city of Nairobi, killed over 30 people. Nobody can persuasively tell any Kenyan that climate change is abstract. It is not. So again, underscoring the potential for lots of research in this area and the critical need to carry out that research to understand the impact of climate change on modern day Turkana Basin. The very last thing I'll say is a quick plug for some upcoming events. First, not this coming Monday, but the following Monday, if you are planning to attend the Zoom meeting for the Research and Innovation Town Hall Series, I will be talking briefly about Turkana Basin Institute at that series. But more exciting, as far as I'm concerned, is our conference that will be held October 22nd. 2025 marks the 20th anniversary of TBI at Stony Brook. Again, it was founded in 2005. We'll be celebrating here at Stony Brook the research and educational impact that TBI has had here at our university. We'll be featuring faculty as well as folks involved in field schools. The provost will talk, TBI Director Emeritus Lawrence Martin will talk. I'd like to extend this invitation to all of you. We'd be very happy to have you join us in this celebration of what is now 2 decades of TBI at Stony Brook University. And with that, I will thank you for having me.
Okay, thank you so much. You have 3 students to ask questions today. Kara, Jared, and Naomi. Jared,
Yeah.
about?
Gotcha.
Go for it.
Great talk. Very, very interesting to learn about all the evolutionary aspects of human life from way back when. So one thing is like, what were some challenges maybe for you or for other like paleoanthropologists face when you're looking at these fragmentary axial skeletons of the Miocene apes? And if those challenges also have limitations to how you are interpreting locomotion and posture in these apes? Like, how does that affect the way you're interpreting these skeletal fragments?
Yeah, so I think, I mean, the biggest consideration is the taphonomic impact on the fossils themselves, right? So you're not, as you mentioned, just finding an entire femur in which you can easily take all of the measurements you need and you can envision its entire morphology and say this clearly looks like a chimpanzee, whereas this clearly looks like a monkey. Instead, you're left with some strange fragment and you're like, okay, what measurements can I possibly get off of this strange fragment? And then keeping in mind that that piece of that fragment, even if you can identify that, okay, this actually looks more ape-like than monkey-like. The thing about the Miocene and the reason it's actually called the planet of the apes is there are a lot more Miocene apes 23 to 5 million years ago than there are today, right? Now we're left with a handful, ourselves, gorillas, chimpanzees, bonobos, orangutans, gibbons. There were more than 50 genera of apes back in the day. And so what that also means is that there are actually no good living analogs for what Miocene apes looked like. Miocene apes were wild. They were doing all kinds of things and eating and moving and looking in all kinds of ways that none of our modern apes, day apes, do. So I'd say one of the biggest challenges is the lack of sort of modern analogs, and it really is abstract in the sense that you don't know, you can't even imagine what the thing is supposed to look like because their bodies are built in ways that are not represented in our current day taxa.
Thank you.
Naomi?
Hi. Very interesting talk, and it was also really cool to learn about TBI's efforts. I wanted to ask, what is your favorite and or, in your opinion, the most important finding that you determined from the NP 64631 postcranial specimens that you found?
Oh, good question. All right, well, let's see. I want to say the lumbar vertebrae. But realistically, I think the thing that has intrigued me the most is the elbow joint, which is represented not only by the capitulum of the distal humerus, but also the radial head. And what we can tell is that this ape actually had really large forearms. So if you look at the proportions, the metrics of the forearms compared to other parts of the body, the forearms seem to be sort of strangely large, again, disproportionate compared to what we see in modern day taxa, such that, and I didn't mention it here, but such that we've actually dubbed this primate Popeye. And so it has sort of its little nickname because it just seems to have these massive arms. So I would say definitely the bones of the arms, but of course, in relation to the other bones of the rest of the body.
Interesting, thank you.
And Kara?
Super interesting. I don't know a lot about fossils, but I really enjoyed that talk.
Neat.
I was just curious if you found anything outstanding or specifically that caught your eye from either side of the lake basin, if there was any differences in skeletons you found. And also, you mentioned that there will be stable isotopes in the future, and I was wondering what measurements you took to solve those.
Sorry, can you repeat the last bit?
Yeah, so you're using stable isotopes in the future. You mentioned that's part of building in the projects. And I was just wondering what measurements for the stable isotopes plan on using and looking at for what.
Got it. Okay, so for the first part, I would say the biggest difference is that out of the sites on the eastern side of the lake, it's best known for sites associated with the Kubi-4 research project, which is where Meave and Richard got their start. But other than that, actually the Miocene sites out there, other than Ciboloy, which is much further south and mostly is characterized by wood, Bullock is really the only other site out there that seems to be terribly fossiliferous, and it actually dates to the early Miocene. So I mentioned that sort of early Miocene, middle Miocene transition. Things look wildly different between the early Miocene and the middle Miocene. You would pick up an animal and be like, oh, this pig in the early Miocene looks nothing like the pigs of the middle Miocene. So I would start with that. You just have sort of completely different taxa that's partially or potentially related to this middle Miocene climatic optimum. To the second part of your question, the stable isotope lab that's going in, I'm not directly working with that lab. That's a lab that is facilitated and made possible by Kevin Uno, his, I think, NSF career grant. Nope, I don't know. Made possible by Kevin Uno and his colleagues. The photo you saw there was with one, John Gatanga, who is his lab manager and works out there at TBI Nairobi at the lab. You can certainly ask Kevin what they plan to do with that lab and what is of immediate importance, but I don't have any direct intentions to do anything with that, although I'll say that Napudet is part of that larger TMP project in which there is a lot of isotope data being analyzed, and I'd be happy to actually turn TMP questions to Greg if he wanted to ask something specific, because one of the PIs of that project is here in this room today. Yes.
Just wondering if you could say a little bit more about how one goes about discerning from a bone fragment something about the range of motion of the hip. I mean, that's something that you mentioned, and just want to hear a little bit more about how you figure it out, to use a Feynman phrase.
Yeah. Well, to put it most simply, it's just sort of basic geometry. In the sense that you have a lot of different shapes of the hip joint, so the femoral head. There are some animals in which the shape of the femoral head is actually kind of cylindrical, such that it's really only adapted, and you can imagine how a cylinder moves, it's really only adapted to sort of have the leg go back and forth. Apes are notable in that those femoral heads tend to be quite spherical and globular. They're really quite round. And as you can imagine, sticking sort of, if you just think about like a peg and socket, that round object into the acetabulum or the joint itself means it can move in all sorts of directions. That's not possible by the shape of the head of something that's more cylindrical. Those sort of just two extremes. But in terms of actually capturing the more nuanced morphology, there's lots of sort of 3D imaging techniques we do in which we can fit surfaces that look at the actual curvature of those surfaces and sort of quantify its globularity. But we know based on living primates that those things do relate, the shape of the head, of the femur, and the types of mobility possible at the hip joint. So for example, all primates, including ourselves, have what's called a ligamentum teres that actually connects the femoral head to the acetabulum. It's partly what's responsible for you not easily dislocating your hip. Orangutans actually don't have a ligamentum teres. So if you look at their femoral heads, it's just like a golf ball with zero sort of impressions or attachments for this ligament. And that allows orangutans, I don't know if you imagine going to a zoo and looking at orangutans moving around their environments. They use their hind limbs almost much like their forelimbs, right? They're able to sort of do all sort of wild things with those hip joints. And so that also relates to how we know they can move their hips around in many ways.
Thank you.
Yeah.
So, do you have any evidence of predation on these bones? Did all these apes just die in place and you only have fragments because things got scattered around and all? Or, you know, were they eaten by something else, and what might they have been? Were predators?
Yeah, this is a great question. So of the fossils that we've recovered ourselves, there's no indication of predation. One thing that I didn't describe in detail is the kind of landscape that Napudet is. Napudet was a volcanic landscape in which there were probably quite frequent disruptive volcanic events. And part of the reason that some of these primates are so well preserved at Napudet is the fact that it is this volcanic landscape. I kind of think about it as like the Pompeii of the Miocene. You can imagine there being this major eruption and then the fossils are just covered. So in a lot of cases, it's really that they got blown up on.
I think we have a question. Karina, do you want to ask a question?
Yeah, can you hear me okay?
No.
No? Oh no.
No.
Oh no.
She said, I mean, she said something, I heard her, but
Oh
I just
dear.
didn't hear it.
I should turn this.
No, I just the, all right, room volume is going up.
Karina, can
could
you-
try again?
Can you hear me now?
Yeah.
Oh, good. Thank you. Thank you so much for your talk. And it's just wonderful to hear all of that exciting activities going on. And I was really interested in a little bit more context on that Miocene optimal warming, and when we showed that graph, we could see that the carbon dioxide was 1,600 parts per million. Obviously, a very different environment there. And when we're thinking about these slow adaptations and morphological changes, are you linking any of these with sort of shifts in diet that may have been driven by climate changes impacting the vegetation communities or anything like that?
Yeah, so one of the aspects of the project is to really investigate these sort of lineage specific changes, and that includes thinking across a broad number of factors that could impact sort of how responsive animals are. So one of the things we're looking at are sort of like large-bodied and small-bodied mammals, assuming that those small-bodied mammals like rodents may be sort of what we call first responders, and that they may be able to adapt more quickly, whereas there may be larger bodied lineages that take much longer. We don't have, there's not at this time, the project is still sort of in its initial stages, direct, we are planning to connect it to factors like diet, but in the ways that we're able to with the fossil record sort of uses these like crude categories of like herbivore and omnivore, et cetera. So the data themselves often don't have really great resolution.
Okay, yeah. Thank you. Thank you.
I think if there are no more questions, then thank you so much.
Yes,
Thank you.